Welcome to Math with Mrs. Bibb. Today we will be discussing special functions, piecewise functions, step functions, which are also called greatest integer functions, and absolute value functions. First, we will define a piecewise defined function, and it's a function written using two or more expressions. And I call those pieces. A piecewise function will have pieces. Example 1, we're going to graph with Desmos the equation you see there. And how to enter it into Desmos is kind of special. You are going to enter, you don't have to enter the y, but you're going to enter the braces. So you'll use a brace. You'll put x less than or equal to 1. So it's that first constraint. So this first constraint right here, hold on. You'll enter it there. In a moment we'll do the second constraint, but we're doing the first one right now. After that first constraint, you put a colon, and then you put the expression x minus 3. So it's the condition that you've put on x minus 3. Then you put a comma, and then you put the next condition, the one I've colored in blue. X is greater than 1, and you put a colon, and you put 2x, and then you end it with a brace. Now let's enter that into Desmos. The brace is there. I guess I entered that earlier. And we're going to do x is less than or equal to 1. And then we're going to put a colon. And then the expression, I think I have z, don't I? Then the expression x minus 3. Then a comma. I think that's the comma. And then x is greater than 1. With a colon. And then the expression 2x. And then close your brace. And there's our piecewise function. It says facts that Desmos does not tell you. Whether or not the beginning of each piece has an open, or a closed or solid circle. You must determine that based on your constraints. The red and the blue that I have highlighted there. Those are called constraints. The ends of most pieces continue forever, so you should sketch arrows on the ends of your, and we can call those rays. That's what those are rays, but some of them aren't rays. Some of them are segments. You could also call them pieces. Okay, so let's draw that. And we can use some points here. Let me go back and get a pointer. Sorry about that. But let me click on that. Hold on, let me make it bigger. We can see it anyway. 1, -2, 0, -3, 1, -4, so I'm going to plot those points. 1, -2, 0, -3, -1, -4. And then this is the piece that is less than or equal to 1, so this would be a solid circle. I really should make that piece bigger, so let me erase and make that piece bigger. So there's that piece. And then the other piece has endpoints of 1, 2. And at 1, 2, it is an open circle since my blue constraint is greater than 1. Next, I have 2, 4, 2, 4, and then 3, 6. And I'm just getting those ordered pairs from this graph. That's where I got them from. And then I'm going to draw that piece, and that is my graph of my piecewise function. And now I want to discuss some key features for this graph. First thing that we'll look at is that the y-intercept of the first piece is -3. And notice there's no x-intercept. So that's some key features that we see. Our domain is all real numbers because if you look at this graph, how far to the left is it going? It's going forever. And how far to the right? Forever. Even here, this is included here and excluded here. So we know it's going forever. So our domain is from -infinity to +infinity. Our range, if we look at our range, looking at our y values, our range is going from -2 forever down and then +2 forever up. So we would say from -infinity to -2 with a bracket because this -2 is solid, union, so we're up here, -infinity to -2, then union 2 with a parenthesis to infinity. And it is increasing for all values of x. So those are some key features that we can discuss about the graph of that piecewise function. Next, we're going to write the constraints that can be used, or the piecewise function that can be used for this problem about a football coach is ordering new jerseys for the new season. The manufacturer charges $88 for each jersey when 5 or fewer are ordered. So to write that, that's our first piece. So let me grab f of x is going to equal the jerseys cost $88 each if 5 or fewer are ordered. So 5 less than or equal to 5 greater than 0. My next piece comes from that next statement, $75 each for an order of 6 to 11 jerseys. So $75 each. We have to consider that 6 to 11 range. You're ordering more than 5, but less than or equal to 11. And I know it said 6, but isn't 6 greater than 5? With a piecewise function, these two pieces here will have this in common. This one will be a closed circle. This one will be open. That would keep it a perfect piecewise function. So we have to consider that. And then for my next piece, $65 each for an order of 12 to 29. So $65 each for an order of 12, so greater than 11, less than or equal to 29. And then $56 each when 30 or more jerseys are ordered. So when 30 or more are ordered, so greater than 29. So that connects all the pieces. These numbers connect all these pieces. Hopefully you can see that, and that will make sense. And our next thing, that was part A of what we needed to do. We needed to write the piecewise function. Our next thing that we want to do is we want to evaluate this function using a few scenarios. So I want to know, what would it cost to purchase 11 jerseys? Well, let's see where that would fit. 11 jerseys would fall in this category here. So I would do $75 times 11. And there's a little trick to that. When you multiply by 11, you write down the ones digit, you add together 7 plus 5, that's 12. You carry the 1, so that should be 825. If you want to check me, you are welcome to do that. But that would be $825. So it would cost $825 to purchase 11 jerseys. And then I want to know the cost to purchase 25 jerseys. So let's figure out what piece this falls into. 25 jerseys would fall here. Greater than 11, less than or equal to 29, so it'd be 65 times 11. No, 65 times 25, sorry about that. So 65 times 25 would be $1,625. And then we want to evaluate the function at f of 29. So there's 3 problems here that you should have written down. The cost to purchase 11 jerseys, the cost to purchase 25 jerseys, and then you should do f of 29. So the question is, which of these formulas do I use? Do I use this formula, 65 times 29, or do I use this formula, 56 times 29? Which one of these is equal to 29? And that would be this one. So you're going to use the 65 times 29 to evaluate that function. So it'd be 65 times 29. And that is $1,885. So f of 29 would be $1,885. And those would be the answers to those questions. Now we're moving on to step function. The definition for a step function, I think I have to change the color. I have white as my color, and I think I need to change that. So a step function is a common piecewise function. That has a graph that is a series of horizontal lines horizontal line segments which may resemble a staircase. The domain is an interval of real numbers. An interval of real numbers. And the range is a discrete set of real numbers. One kind is called the greatest integer function. And we are going to graph that using Desmos. Graph f of x equals, and then those double brackets around that expression indicate that you have a step function. To type it into Desmos, and this is so strange, I had to Google it, but to type it into Desmos, you don't have to enter y, but I'm going to write y equals. You type the word floor, F-L-O-O-R, and then in parentheses you put 2x minus 1. And I'm not going to have you actually draw that, but we are going to graph it to see what it looks like in Desmos. And I should have brought up that picture. I will do that right now. Okay. I think I can add a link right now where I'm at, browser. Yes. So I'm going to type floor, F-L-O-O-R. Whoops. And then in parentheses, I'm going to put 2x minus 1. And close the parentheses. And then you can see that series of steps in the picture. One thing you cannot tell from this graph from Desmos is that the ends, let me see if I can write with my pencil, the ends to the left are all solid circles. That's how this greatest integer function works. This is the integer. This integer is the answer for that interval that's represented by that little red dash. And then in order for it to be a function, if this is a whoopsie, how did that happen? If this is a function, for this to be a function, this has to be an open circle here because this is a closed circle. So open, all of these have open circles. But again, you did not have to graph this. Now let's talk about what this means. We'll talk about domain and range. Our domain, how far left and right could this graph go? Well, if we extend it, if I move mine, it's going to take away my little red dots that I have there. But if we extend it forever, this graph would go forever to the left and forever to the right. So our domain is all real numbers or negative infinity to positive infinity. And then our range is the set of integers, because the greatest integer function only produces an integer. The integer that is produced here at this step, is -1, -2, -3, -4. So this one is -4. This one is -3. This one is -2. This one is -1 and 0 and 1 and 2 and 3 and 4, so on and so forth. So that's why the range is limited to just integers. I want to move that graph down so I can actually write. So my little dots are going to be left behind, but that's okay. All right, so it says state the domain and the range. The domain is from negative infinity to positive infinity. And my range is the set of integers. And so I'm just going to say the set of integers. There is a way to write that in set builder notation, but we'll just say the set of integers because the answer would be an integer, the greatest integer function. Next, absolute value function. To define an absolute value function, it's a function that contains an algebraic expression within absolute value symbols. So a function that contains an algebraic expression within absolute value symbols. The parent function for an absolute value function is f of x equals the absolute value of x. Or it can be written as a piecewise function because it's two linear expressions that meet together at one point. So it can be written as a piecewise function. F of x equals x if x is greater than or equal to 0, and f of x equals negative x if x is less than 0. Those are both acceptable for absolute value functions. To be honest, this is the one that's used most regularly, not the piecewise function. The domain for absolute value functions written in this form is all real numbers or negative infinity to positive infinity. The range is all negative real numbers, all non-negative real numbers, which how do we write that? Non-negative would be from 0 to infinity. And the x and y-intercept are both 0. The x-intercept is 0, the y-intercept is 0. Or it can be written as the ordered pair 0, 0. We are going to graph that with Desmos, and I think this should say example 4. So please correct that on your paper. This should say example 4. To enter it, you do not have to enter y equals. You can, it doesn't matter, but you do not have to enter y equals. There is an absolute value button. So you just press that absolute value. It's right above the ABC. And then you're going to type in 1/2, so 1 divided by 2. And then make sure you click beside of it so that the variable is beside the fraction. So 1/2 x plus 2. Now let's look at ordered pairs. I'm going to plot 0, 2. It looks like 2, 1, 2, 3, 2, 3. Negative 1, negative 2, negative 2, 3. So I'm going to plot 0, 2. 0, 2, 2, 1, 2, 3, and negative 2, 3. And I'm going to draw, absolute value looks like a V. I'm going to draw that V. That's how you graph with Desmos an absolute value function. And the last thing we're going to do is we're going to write the piecewise function for each of the graphs below. If you will notice, and I'm going to write underneath each of them right now, if you will notice, the first function has 2 pieces. So I'm going to set it up for 2 pieces. The second function has 3 pieces. I'm going to call that g of x. That way it's different. That's why we have function notation, is to have different kinds. And there's 3 pieces, 1, 2, 3. And the last one I'm going to call h of x. There's only 2 pieces there. Okay, the first thing I'm going to do is name the slope and the y-intercept of each of these. My slope for this first piece here is up 1 over 1, up 1 over 1, up 1. So my slope is -1, and the y-intercept is -1. So in this blank down here, I'm going to put in the form mx plus b. So mx plus b. That's my expression if x is less than or equal to 0. Because here is the ordered pair 0, -1, and x is less than or equal to 0, and it's equal to because it's solid. And then this one is going to be if x is greater than 0, because it's open, and x is still 0 there. The slope, up 1 over 1, up 1 over 1, is +1, and the y-intercept is +2. So remember mx plus b, so mx plus b. That is the answer to the first one. This whole thing is the equation of that piecewise function. Now for my next one, I work on my pieces from left to right, so I'll do this one first, this one second, and this one third. What is the slope of this one? Up 1, left 1, up 1, left 1. So my slope is -1, and then down 1. What would be my y-intercept? It would be -2. It's not currently -2, but it would be -2. So you can definitely count. Please don't write in your books, but do trace in the air, or flip your pencil over and use your eraser and trace to find that y-intercept. So that y-intercept would be -2, I think we said. So write it in the form mx plus b, so -1x minus 2 if x is less than or equal to -2, because that's what x is here, -2, 0, and it's solid. And now for this next one, my slope is 0 because it's a horizontal line, and the y-intercept is 2. So y equals mx plus b. Oops, I was about to write the y. So 2, it is 2 if x is between -2 and 1. Between -2 and 1. So if x is between -2 and +1. And both of those ends are open, that's why they're both less than symbols. And now for the next one, my slope is up 1, 2 over 1. Up 2 over 1, up 2 over 1. So my slope is 2 over 1, or 2, and my y-intercept would be down 2 over 1, -3. So mx plus b. And that would be if x is greater than or equal to 1. So that's the answer for the second piecewise function. And now the last one, there's 2 pieces. 2 pieces. The slope here is 0 since it's a horizontal line. The y-intercept is -3. So it's -3 if x is less than or equal to 0. Because here's where x is at. It's at 0, -3, and then x is less than or equal to 0 here. And then, can you tell that's 0, I hope? For the next one, my slope is, I'll start down here, up 3 over 1, up 1, 2, 3, yes. So my slope is -3, and then my y-intercept is +3. So mx plus b if x is greater than 0. And that's how you write that piecewise function. I hope that helps, and I hope you have a wonderful day.